Yeah. Okay. Yeah. So first of all, I want to thank the organizers for inviting me for a talk, and also thanks to all of you for choosing this session over the others. So there are lots of other interesting talks going on. So I hope I can live up to some of your expectations. I'll talk about this topic of shaping kinetic magnetism by frustration. I'm not really an expert on magnetism, so this will be sort of outsider's point of view. I'm more of a dynamics open quantum systems person. But sort of the broader question we are interested in this problem is that is this thing in the box. So how does quantum mechanical ordering of a many body system how is that governed by the underlying geometry? And more specifically, can you do local changes in the connectivity between sites and in order to shape the many body collective ordering of some quantum mechanical system? So that's the broader question. And this is partly motivated by developments in network science in classical systems. So depending on how people are connected, information spreads very differently, diseases and so on. And partly the motivation is to ask similar questions in quantum systems, which may have applications in quantum devices and such. So as you can imagine, this is quite an open-ended question. And so my postdoc Revati, this was mainly done by her, so she deserves a lot of credit to look at the problem from different points of view and take it to a satisfactory conclusion. Yeah, so let me first start with introducing kinetic magnetism, as it may not be familiar with everyone in the audience. So I'll start from the Hubbard model, which you can define on any geometry, doesn't have to be a regular square lattice. And I have these bonds which represent hopping between, an upspin or a downspin can hop across these bonds with some tunneling amplitude T. And if two of them come up at the same site, they have some interaction energy U. And I largely consider the limit where U is much bigger than T, so that prevents double occupancies, so things like that, because that costs a lot of energy. And so the Hamiltonian actually can be written in two parts in this limit. One is this hopping part subject to this hardcore constraint of no double occupancy, which is the kinetic part. Plus there can be processes where a spin up goes from site A to site B, and at the same time spin down comes from site B to site A. That also is energy conserving, so you get these virtual hopping processes, and you just get an antiferromagnetic Heisenberg coupling between these sites connected by bonds. Right? So the Hamiltonian becomes this sort of TJ model. And so if you work at half filling, which is that you exactly have the same number of fermions as the total number of lattice sites, then no hopping is allowed, because you basically have to have one particle per site. So this part goes away completely, and you are left with the exchange part, which gives you antiferromagnetism. So it's just a Heisenberg antiferromagnetism. But then if you add a hole on top of half filling, then you unlock some of the hopping processes, because the hole can hop right from one side to the other. And then if you consider the limit of taking U by T goes to infinity, then this the exchange term completely drops out. So you are left with just the hole hopping in the background of some spins. Some of them spin up and some of them spin down. But still, it turns out rather amazingly, then just this hole hopping can select a collective magnetic order for the system, right? Because the hole can take different paths through the lattice, and these different paths will interfere destructively or constructively depending on the spin background. And so it turns out that so this hole hopping will favor one type of magnetic ordering relative to the other depending on the lattice topology. So this is just magnetism coming from the hopping of the hole alone. And when I first heard about it a few years back, it was sort of mind-blowing to me that it's just a hopping of a particle can give rise to a collective magnetic order. And so the question was that we know that these paths are dictated by the underlying lattice. So if I change the lattice geometry, then all of these paths will get changed. And so the magnetic ordering that is favored by this kinetic part will be also different. So the central question is, how does that happen? So this brings us to the idea of frustration. All of you are familiar with this frustration that comes from exchange antiferromagnetism. So if you want to anti-align all the bonds, spins with respect to all the bonds, then this is possible to do in a square like this, but it's not possible to do in a triangle. And so that gives rise to frustration. You cannot satisfy all the bonds simultaneously. That is frustration coming from exchange coupling. But this kinetic thing can also give rise to frustration, right? So if you just have the hole hopping like this, So one thing is that the hole hops with negative the tunneling amplitude of the electron, because C and C dagger anti-commutes. And so you can sort of think of it like this, that every time a hole hops across a bond, it changes the spin, because the spin has to hop from this side to this side. So the spin configuration gets changed, but also the wave function gets a minus sign, because the hole is hopping with negative hopping amplitude. And so if you start from a state like this, a ferromagnetic background of a single square with a hole sitting at one side, I make one hop, so I'll see what the hole does by moving around this single loop that is present here. So if you make one hop, the hole comes here, the upspin goes there, you get a minus sign, then you do one more, it becomes a plus, and the hole comes here, and then you repeat it like this, and you come back to the original configuration with the same sign, with plus sign. Right? So that means that you are getting a constructive interference by moving through this loop. And this is not only true for a single square, this will be true whenever you have some even-sided loops only, and you have a ferromagnetic background like this. So if you move a hole around any of those loops, you will come back exactly to the original configuration with the same sign. And so this idea was pointed out, based on this, we know that in all bipartite graphs, which only has such even loops, the ground state will be ferromagnetic, because that's what gives constructive interference. But that is no longer true if you have a triangle, because you'll see that you'll get back to the same configuration with the minus sign, so you actually get destructive interference for ferro background under the same process. So we will say that the ferromagnetic state is frustrated because of this destructive interference. Right? So on any non-bipartite graphs which will have such odd loops, you will not have ferromagnetic ground state in general. So then the question is, what is the ground state under such frustrated cases? If you have a single triangle, then there is an exact state which gives you full constructive interference, which is the singlet state. Right? So you have the hole at one side, and you have a singlet, which I am calling S23 of the other two sides. Then the hole hops from 1 to 1 and 1 to 2. So you have to basically permute, swap 2 for 1 in the singlet state, and you get a minus sign, and then you repeat this process. And because the singlet is antisymmetric with respect to its indices, you actually come back to the exact same state that you started from. So you get constructive interference this way by having a singlet on one bond. And so it turns out that the ground state will be just a superposition of all these three states, equal superposition. That is the exact ground state. If you have an extended lattice, right, so not just a single triangle but multiple triangles or things like these, then there are multiple loops involved, not just a single loop, and so generically there is no many body state which gives you constructive interference on all those loops. It's a competition of different interferences, and depending on the geometry, so people have done this on regular lattices or sort of planar cactus-like graphs like this, and they have found that the ordering depends on geometry. So the most widely studied case is the triangular lattice, where you get this 120-degree classical antiferromagnetic order, where if you take any given bond, that is quite far from a singlet state. On the other hand, if you have these sort of what is called a triangular cactus, which is basically a Kagome lattice with some bonds missing, it's like corner sharing triangles, there also the ground state can be solved exactly, and you get some resonating valence bond state. So the hole is sitting here, and these are singlet covering, this is the singlet covering of the remaining part, and then the hole can go to some other position, then you'll again have some singlet covering. It's a massive superposition of such coverings. And on a pyrochlore lattice, even for a given hole position, you can have these singlets will fluctuate between bonds. So it's like a liquid sort of RBB state. Right? So the message is that even for extended sort of regular or semi-regular lattices, the ordering will depend on, the exact ordering will depend on geometry. And some of these predictions have been tested very recently in experiments. So these are, I think, 2024. So this is with a quantum dot plaquette, and these are with cold atoms in a triangular lattice, where people have seen both ferro and antiferro sort of ordering based on these two arguments, and they can reach u by t as high as 72, so which is really a good approximation to ignoring the exchange term. But the question I want to ask, therefore, is if I have some non-regular lattice, so the frustration level is not uniform across the lattice, I can have more frustration here compared to there, then what will be the ordering, right, on general lattices or graphs? And let me give the key takeaway right away, that if you have frustration centers like this, we find very generally that these centers bind singlets, while the whole remains shared between all the sides. Right? So that's the key message, and what that allows you to do is modify the local topology of the lattice to change to bind a singlet there, to change the ordering coming from the many body system. And also importantly, this is not found in exchange magnetism. At least if you have equal bonds, equal coupling on all the bonds, then you find that the spin alignment, even local spin alignment or global spin alignment, is not as sensitive to these frustration centers, much less sensitive than this case. Right? So this quantum mechanical interference is really letting you do such things. Okay, so that's my key message. So I'll now go through some of the results. So we take a bottom-up approach where we start from a simple lattice like this, a single square with diagonal bonds, and then we make it successively more complicated to establish the generality. That's sort of the idea. Some of this will be analytical, some of this are based on exact diagonalization, and some are DMRG. I'll point out those where they come. So if you have a frustrated square like this, the green diagonal bonds are what's making it frustrated for the ferro ordering. Then when T prime is small compared to T, then you just have this ferromagnetic ordering, right? This Nagaoka ferromagnet, and the ground state is an equal superposition of the states we found earlier. And the energy of this has this expression, so you see that this increases with T prime, right? So this will be the overall ground state only for small T prime. As you increase T prime relative to T, this ceases to be the ground state beyond a particular value of T prime over T. If you do this phase diagram, so you find the ground state as a function of T prime over T, or actually we are parametrizing it as in terms of this U, T prime is U, T is 1 minus U, U goes from 0 to 1. Then you see that for small u or small T prime we have this ferro behavior, but then this S total was 3 by 2 in this case, maximum value. And then beyond this critical value of u, S total is actually half, which is the lowest S total you can have in this system. If you look at, but the state actually is not the same throughout this region, and that's reflected in the parity. So this setup is of course symmetric with respect to reflection about x-axis and y-axis. So you have these two parity operators which can be either plus or minus. And so if you track the parity of the ground state, you see that there is a jump in parity. Here it's different from there. Right? So actually there are 3 regions. So we discussed this region. If I go to region 3, which is the strongly frustrated large T prime region, there you no longer have just all spins pointing up. Right? We know that the ground state has one magnon. So then the state, you expand the Hilbert space. It's not just the position of the hole that matters. You also have position of the downspin, with 2 upspins and 1 downspin, where the downspin is. So your basis states become, from 4 it expands to 12 such basis states. And you can draw a Hilbert space graph corresponding to your Hamiltonian, where this first index is the position of the hole, and the second one is the position of the downspin. Right? So each of these bonds are coming from one of these bonds. So if you take this green bond, for example, that represents the hole hopping between 1 and 4, which is this diagonal bond. Whereas if I take 4, 2 and 3, 2, that is hopping between 4 and 3, this black bond. So it is just an expanded, so you can think of it as a single particle problem on this expanded Hilbert space graph. And again, each of the bonds you have here is trying to get opposite amplitudes on the 2 sides of the wave function, right? So plus minus type. So because the green bonds are more dominant with respect to the black bonds, so T prime is bigger, it helps to satisfy all the green bonds, right? So how do you satisfy all the green bonds? You give the plus, opposite amplitudes across the green bonds. All of them are symmetric, and this one you cannot give. If you give minus, you cannot satisfy this green bond. So the best you can do is actually make the amplitude 0 at these 4 sites, and the black bonds also don't have equal sign across them. So this is sort of the minimum energy as far as you can get, minimally frustrated setup. And if you actually write down in terms of these basis states, what you find is that this state is actually equivalent to creating a singlet between 2 and 3, singlet here, and the hole hopping between 1 and 4 here. This is the sketch, right? Minus the opposite. You have singlet on this bond and hole hopping between that bond. That is the exact ground state, and we call this a sort of cross dimer state because of this obvious structure. And this also has some simple expression for energy. This diagonal singlet correlation also reflected in the spin correlation between two sides. So if you look track si.sj, you find negative value between 1 and 4 and negative value between 2 and 3, whereas there is no strong correlation between 1 and 3, for example. Right? So this is directly reflecting the singlet structure. This is region 3. If you go to region 2, the state is more complicated. So T is bigger than T prime here. So you want to satisfy the black bonds more at the cost of frustrating some of the green bonds. And this turns out to be the exact state with some superposition of these two parts where x is a fraction, x is smaller than 1. So basically you are dominated by this part of the wave function where you see that I have a singlet between 1 and 2 and hole hopping between 3 and 4 minus the opposite. So these have vertical singlet correlations which are also reflected in the spin si.sj type things. This is the sketch of the wave function you get in region 2. So anyway, so this is the 3 regions for a single frustrated plaquette, and the main message is that if you make the frustration large enough, you start binding singlets, and it could be diagonal or vertical depending on the strength of the frustration. Okay, so now we embed such a thing in at the center of a ladder, and again you will have some phase diagram as I tune these two ratio T prime over T. And again, I have 3 regions, but now S total can go down in steps by 2, right? Because S total is not limited. The maximum S total was 3 halves in the previous case, which is not the case here. So you again have no magnons here, 1 magnon and 2 magnons in these increasingly frustrated regimes. And you can track what is the hole density and magnon density in these regimes, and what you find is that as you increase U, as you increase this frustrated hopping, the hole gets more and more localized on this plaquette, on the central plaquette. And throughout this range of U, in all 3 regions, whatever magnon you have is strongly bound to the central plaquette. So here you have 1 magnon bound to this thing, and you have 2 magnons also bound to this central plaquette. So irrespective of whether the hole is spread or not, the magnon is always strongly bound to the frustrated plaquette, and this can be sort of explained by this whole magnon attraction. So there's a separate study which shows that you can lower energy by binding the hole with a magnon than having them move separately. So there's an effective attraction that you get in the presence of frustration, which is only present here. So that's why the magnon is getting bound to the central plaquette. That's one way to understand it. So and this is a sketch of the 2 regions. So the hole is delocalized in region 2, and you have vertical singlet correlations, 1 vertical singlet in a superposition of these 2. And in region 3, where you have sufficiently large frustration, then you have the hole gets localized, and also you have this cross dimer type state, 2 diagonal singlets in the frustrated plaquette. Okay, next we go to again increase the complexity. Now you have 2 such frustrated plaquettes separated by some distance 2p, and if you make p small enough, they will start interacting with each other. You can get collective effects. That's the idea. So as a function of p as well as a function of this u, which is the ratio basically, you get some phase diagram with now 5 regions, and I have colored these differently because in regions 2 and 5, the 2 frustrated plaquettes behave as if they are independent. So they don't see the effect of the other plaquette. And in region 3 and 4, there are strong collective effects. So the background, so the neighborhood of one plaquette is strongly affected by the existence of the other plaquette. Right? So let me skip this thing, and this is the sketch. In region 2, what you have is the hole is delocalized throughout the system, and each of them is binding 1 vertical singlet. Right? So with respect to one of the plaquettes, this is what they would have done irrespective of the existence of the other. In region 5, on the other hand, the hole gets localized or sort of trapped on one of these plaquettes, and that binds 2 diagonal singlets. Right? While the other plaquette you see is completely aligned, so there's a ferromagnetic, all spins are pointing up here. So you have 2 degenerate such ground states. Yeah. On the other hand, in region 4, this is a collective region. So the hole is shared between the 2 frustrated plaquettes. Actually, the tail of the wave function is spreads enough to see the influence of this plaquette from here. Right? So what happens is the hole is shared between the 2, and each of them is like binding 2 diagonal singlets. If you look at the wave function, you see that it is of this form where the hole is here, and this part does not really have a hole, but it has a singlet sort of state. There is no reason for this plaquette to bind a singlet if the hole is here. Right? So this is a collective sort of behavior where each of them sort of add up in terms of the number of singlets. You also see that in the correlations. And region 3 you get something even stranger, which is that you get a domain wall. The spins are pointing up here, then all the way down here, and then up here. These two sort of form pin domain walls, and the hole is confined in between. We don't really have a simple explanation for this, but this is clearly a collective effect because this doesn't happen at the level of a single placket. Right? And also the parameter region it happens is very narrow. Okay, so now I'll expand to other geometries, but what we saw from here is that if you have these ladder sort of geometries for sufficiently large frustration, you get bind vertical or diagonal singlets. So now suppose I have a rectangular grid like this, and I start adding diagonal bonds randomly. Right? So I'll pick some diagonal, add a bond there, they pick another diagonal, add a bond there, and so on. And for simplicity, I will consider the case where t prime is t. Right? So all the hoppings are equal, but that you have these extra diagonals appearing. So in that case, what you find is a very strong result. Suppose you track the total spin of the ground state as a function of these number of diagonal bonds. You find that every time you add a diagonal bond, it comes down in steps of 1. Right? That's a strong signature. Each of these bonds is binding a singlet and bringing down the total magnetization. This is subject to a constraint that no two diagonals share the same site. So things like this. And if you keep doing this, you will eventually get a Shastri-Sutherland lattice. So you get some exact one-to-one correlation between the number of diagonals and S total. And even if you don't impose this constraint, suppose I don't care about sharing sites and so on, I just pick randomly diagonals which can share sites also, then it's not exact, but it's more or less, it's a strong, so this black, so gray background is showing the distribution of S total you get from this random set, and the dots you get are the mean values of S total, right? So it more or less goes down in steps of 1. And if you look at the correlations, Si.Sj on these bonds, you find that these diagonal bonds are strongly blue, so anti-aligned, whereas the other ones are red, they are aligned. While the hole is shared, you have the hole here also and as well as here. Right, so that's the more general scenario. And now finally we go to random graphs. So you are not even in a planar grid. Suppose I have some random graph like this. There is no well-defined frustration center here, but you can count triangles and rectangles on this graph. And you can ask how is the total spin or the spin alignment across these bonds connected to the amount of frustration locally, right? So if you do it globally, correlation with S total, you find strong positive correlation with number of, strong negative correlation with number of odd loops, and strong positive correlation with the numbers of even loops. And that also happens locally. If you ask a given bond, how many triangles is that a bond a part of, and so on. So you can use this to if you control the minimum loop size of the graph, you can make the total spin distribution swing wildly back and forth like this. And that's sort of reflecting this underneath singlet binding. Yeah, and as I said before, in contrast, it does not happen in exchange magnetism. I won't go into the details of this. And finally, we proposed some protocol for realizing these diagonal bonds in cold atomic setups, which I've already observed some of these phases. Essentially, the idea is to focus a laser beam to mediate some diagonal coupling, and this sort of works for a large range of parameters, which you can find in detail in our paper. And all of this is part of a broader story of networks. So you can ask similar questions about antiferromagnetism. Here we show that you can get just ergodicity breaking solely coming from the connectivity without having any disorder, and Dona has a poster on this. And finally, Revati has already given a talk about producing multipartite entangled states by tuning these networks and local driving. Okay, so I'll end with this. Oh, I had one more slide. It's not coming up. Yeah, this one. So this is the single one-line message and some cartoon. There are of course lots of open questions one can ask. And so on. Thanks.
Thanks for that. How does the effective Hilbert-Swiss dimension scales here?
Hilbert-Swiss dimension. You just have to count the number of upspins and downspins and different ways of placing them on your lattice. Right? So if you have n sites and you just pick the positions of the hole, pick one position of the hole, and pick and count how many ways you can distribute the downspins in the remaining positions. So that I think it eventually scales exponentially, but I don't recall exactly what the numbers. It is exponential. So that's why we could go up to 20 sites for these random graphs, because otherwise it was getting.
Very nice, very provocative.
Thanks.
So, you do break time reversal, and I was wondering for the fictitious particle moving on the graph, if you break time reversal, you're allowed to have complex phases.
You can, yeah. In fact, there are studies also. If
You have not found this, like these so-called orbital.
So we have taken these to be real tunneling amplitudes, but you can make them complex. In fact, there are studies which look at square lattices where each of the plaquette there's a flux threaded through each of the plaquettes, which makes the hoppings complex, and you can turn the ground state from ferromagnetic to antiferromagnetic that way by tuning the phi per plaquette. So there's already a study, in fact, on such things. I don't remember. It's 2005 a PRL, but I don't remember the authors, unfortunately. But there are some such ideas there.